Okay, in this video I'd like to practice some more with our left and right hand Riemann sums, as well as discuss a little bit more about sigma notation. In this first example, we're being asked to find the area underneath a sine curve, and the area for which we need to find is the region bounded by the graph sine of x and the x-axis between the x values of 0 and pi over 2. So as a reminder, the sine function looks something like this, and it'll continue its wave pattern. The value pi over 2 is actually right here. That's the x value of pi over 2, and here, of course, is the x value of 0. So when we need to find the area underneath the sine curve between the sine function, the x-axis, x equals 0, and x equals pi over 2, we're just talking about this region in gray. Now this problem does go on to say that we are going to find a left-hand sum and a right-hand sum. And they also tell us that we're using 6 subintervals. N equals 6 subintervals. We can use any value of n that we choose. In this case, we're using 6. Now don't forget that the method for finding the left-hand sum, we called it LHS in class, is simply the change in x times the initial y value up to the second to last y value. And for our right-hand sum, we're using the change in x value from y sub 1, which is technically the second point, all the way up to the very last point. Now we could create a table here and identify the y values. I'm actually going to sketch a more precise graph. So I've created a pair of axes here that are 12 units wide and 8 units tall. I'll mark this as a half and this as 1 on the y-axis. And of course here is 0 for both the x and the y-axis. I'm going to mark this point as pi over 2. Now we need 6 subintervals. That's why I chose 12 grid lines. It's easy to make 6 of these subintervals. And we just need to consider if I had the distance pi over 2 divided by 6, then each of these subintervals has a width of pi over 12. So I could label this as 1 pi over 12 and 2 pi over 12 and 3 pi over 12 and so on. But I'm going to go ahead and simplify these fractions. And several of these entries, 0, pi over 6, pi over 4, pi over 3, and pi over 2, those are values that hopefully you had memorized and still remember from the unit circle. Pi over 12 and 5 pi over 12 is not, or are not, values that are typically memorized from the unit circle. Now off screen I did use a calculator to find the decimal equivalents of each of these functions. And I went ahead and plotted them here so that when we sketch the curve to connect these points, we've got as accurate of a sketch as we can produce. All right, so again, our goal is to find the area underneath this curve, and we're going to use left and right hand sums. For the left hand sum, we're again starting with our initial function result here. And we're going up to the second to last function result, which is here. So this is the region that we're using for our left-hand sums. And if I draw the rectangles associated with the left-hand sums, they should look something like this. Now, the function is an increasing function on this domain, so the left-hand sum should be and will be an underestimate. We'll find the value for that in just a second. Now our right-hand sums start at this second data point and they go up to the very last one. That's how we're going to obtain our right-hand sum. And if I was drawing rectangles based on the right-hand data points, they would look something like this. And here again, since the function is increasing, you should notice that the right-hand data sums, or I'm sorry, the right-hand sum will be an overestimate for the area underneath the curve. Each of these rectangles are taller than the height of the function itself. So now that we have a visual representation of what's happening here, let's come back to the functions themselves and talk a little bit more about that left-hand sum. Well, as we saw the change in x, the width of each of these rectangles is pi over 12. And the first y result, well, that occurred right here. That's the function result at an x value of 0. And the second would be the function result, or sine, evaluated at pi over 12. That's not something that I know, so I'll rely on the calculator to evaluate that. Then sine of pi over 6, which is 0.5, or I'm going to go ahead and write it as a fraction, a half. Sine of pi over 4, radical 2 over 2. Now, these aren't helpful for us in graph, but as far as, claiming the results of the trig function, it doesn't hurt to write these as fractions. I'm going to have to use a calculator to evaluate this statement anyway. Now the last value here is sine evaluated at 5 pi over 12. And a quick check should show 1, 2, 3, 4, 5, 6 values. So those 6 values are the numbers needed to generate our left-hand sum. We would do something very similar for the right-hand sum. The width is pi over 12, and we're not using 0 this time. We're starting at sine of pi over 12 plus all of the same content, including sine of 5 pi over 12. But this time we're ending at sine of pi over 2, which calculates out to be 1. So I'm going to use a calculator to evaluate both of these phrases, and I'll do that off screen. And the area for the left-hand sum calculated out to be 0.8634, and the right-hand sum was 1.1252. Now we've already addressed the fact that the left-hand sum in an increasing function is an underestimate, and the right-hand sum in an increasing function is an overestimate. By the end of this week, you're going to know how to evaluate this precisely, and you'll find that the actual area in this case is precisely 1. So we had an underestimate and an overestimate. By the end of this week, we're going to learn how to find this area precisely, and we'll see at that time that the area is equal to 1. Now in this next example, to the left here on the second row, we need to approximate the area underneath this curve. We don't know the function that's defining that shape, but we do have a relatively nice graph to work with. The function exists on the interval from 0 to 6, and we're splitting that interval into 3 subintervals. And we need to find the left and the right-hand sums to identify these two approximations. So if our interval exists between 0 and 6, and we need 3 subintervals, well, I'll just take 6 and divide that by 3, and we see that the width of each subinterval is 2. But you can also visually establish that as well. I'm going to use dotted lines to represent the sides of our triangles. I should say rectangles, not triangles. So this gives me the walls of each rectangle. And then I'm also going to note the function value. Since we don't have the actual equation that generated this set of functions, it's nice to see that each of the function values do land on whole numbers. In the interest of time, I'm not going to draw the entire rectangle, but I will note that for left-hand sums, I need this first, second, and third data point. For the right-hand sums, I need this second, third, and fourth data point. Now here again for the left-hand data sum, we need our delta x, which in this case is 2, and the first function result, which is 1, plus the second, which looks to be 6, plus the third, which appears to be 9, and again 1, 2, 3 sub intervals. For our right-hand sum, delta x, 6 plus 9, that's our second and third result. Now for our final result, which appears to be 11, and we can evaluate these either by hand or with a calculator if needed. And the left-hand sum comes out to be 32. The right-hand sum comes out to be 52. And if you recall from class, when we take the average, this is what's known as a trapezoid sum, TS, THS, I forget what we called it in class, but the trapezoid sum would be the average of the two, 52 plus 32 divided by 2, which is 42 square units. And we have no way of knowing the precise area underneath this curve because we don't have the function that created this curve. But knowing that there are some overestimates and underestimates built into this function, I feel fairly confident that we've got a pretty decent area computed at this point. We could make our estimate better by increasing the number of intervals. We could go to, say, a 6 subinterval, and we can compute our results from there. But I'll leave that up to you to try to see if you can do a better job than this. I don't think I need to work through number 3 in this video. We have a table. The left-hand sum comes from these data points. The right-hand sum comes from these data points. So you could use those to produce a lower and an upper estimate, and you could also sketch this. What I will say, though, is that since the function is decreasing this time, I think our left-hand sum is actually going to be our upper estimate, and our right-hand sum is going to be a lower estimate this time. That's because the graph of the function is decreasing. Now, as a preview for a discussion we're going to have later this week, there's yet another Riemann sum or approximation for area under a curve, and that's what we call a midpoint sum, MPS. With a midpoint sum, we have our subintervals. In this case, we've got 5 subintervals on the large interval from 0 to 10. So that means that our delta x is 2. And you can see that each of the subintervals had been marked here 2 units apart. But instead of using the left or the right-hand side of those intervals to generate the height of the rectangle, what we have to do is go to the center, exactly in the middle between them. And it's the middle of these intervals that's used to generate the height of our rectangles. And hopefully you can see the value or the benefit in that. If we generate the height of the rectangle based on the middle of a interval, well, we have ourselves a built-in under and over estimate within that one interval. We don't have to go through 2 computations in order to get our over and under estimate. You may also notice that depending on the shape of the function itself, this overestimate and the underestimate within an interval do a pretty nice job of canceling each other out. It's not perfect, but we do get a pretty nice estimate based on this. Now, this midpoint sum is not the same as a trapezoid sum. So I want to make that clear. The trapezoid sum would result in a different area most of the time. But again, this midpoint sum, it's another opportunity for us to approximate the area of a region. Now, as far as the formula for a midpoint sum goes, well, again, each rectangle has a width, an interval width or subinterval width of delta x, but instead of using y sub 0 up to y sub n minus 1 or y sub 1 up to y sub n, we're going on these half increments. And that can be a bit misleading. We're not saying that the x values or the resulting y computations are based on an x value of a half or something like that, but the halfway point within the interval. So in this case, we're using the number 1, 3, 5, 7, and 9 as our x values to generate our function results to compute the area. So when I use an x value of 1, 100 minus 1 squared is 99, 100 minus 3 squared, 100 minus 5 squared, 7 squared, and 9 squared. So this is the setup. We have, again, 5 computed results for our 5 subintervals. And the result comes out to be 670. So the approximated area underneath this curve is 670 square units. And to finish out the video, just a quick conversation about sigma notation. Remember what I said last week, that this sigma symbol simply means repeated sums. And when we see the sigma notation, we're usually given a lower and an upper boundary or limit or boundary of summation. And then we're also supplied a function to which we would apply these boundaries. So in part A, we're essentially saying find the sum of all k values for k values from 1 to 10. So the sum would literally look like this: 1 plus 2 plus 3 all the way up to 10. That's really what this notation is asking us to do. And I don't have a quick way to compute this, but knowing how to set it up and determining how to evaluate this is most of the problem. Now, some of these do have neat patterns to them, like the sum of integers. You could add the outer two values and then the next outer two and so on, and determine how many pairs there are, and that should give you an idea of how to compute this result, but they don't always work that nicely. Now, another thing that I'll add, if I didn't make this clear before, these k values are integer or natural numbers, so we don't concern ourselves with k values that are decimals or anything like that. If I'm trying to sum part B, I need to find 2 times 1 plus 1, that's my first entry, plus 2 times 2 plus 1, all the way up to 2 times 6 plus 1, and so on. So hopefully that makes a little bit more sense to you. We don't have to use k as our boundary of summation. We can use n. Sometimes we use I or even j, but that's the process for finding sums using sigma notation. Now, the last type of problem that we see in this handout today is it's kind of an interesting challenge. See if you can write summation notation to identify the sum of this series or these series. And in part A, we have the odd values from 1 to 99, so 1 plus 3 plus 5, so on. And so the challenge is, can you come up with some sort of sigma notation that would add up all of these values? Well, there's a clue here saying that answers are not unique. There are more than one, or often more than one way to write this summation. In this particular case, I'm going to say something like this, that if we take 2n plus 1 for all n values from 0 to 49, well, that's the formula, or that's the summation that would account for the sum of all of these values. Now, again, you could have modified this if you had said something like 2n minus 1, then starting from 1 and going up to 50, that would suffice as well. But usually the trick in these problems is coming up with a nice formula that would generate these numbers, and then accounting for the boundaries, well, that seems to fall into place naturally. So I'm going to stop here. The video is getting a little bit longer than I had expected, and I would challenge you to finish the problems that I didn't complete in the video, and be prepared to ask questions when we see each other next. Thanks for watching.